Three. Welcome back, everyone, to another episode of METI with a fantastic researcher. Today's fantastic researcher is Suradeep, coming to us from University of Maryland, and he's collaborating with Princeton University as well. And he will and the University of Central Florida. And then he will talk to us and teach us about a unified perspective of reward design and policy alignment in reinforcement learning. Suradeep, I've known you for a while. I'm very excited you started your PhD and really happy that you have the time to join us today. Yeah, the floor is yours. Please go ahead.
Yeah, thanks a lot, Hatham, for the introduction. And we have worked together for a good amount of time, and I have learned a lot from both Hatham and Rasul about Bayesian optimization and first order, second order methods, and a lot in those areas, sample efficient BO that we were trying to do. And I'm really excited and glad that I could be a part and just have some thoughts and discussions around this. So, okay, so maybe I'll just start. So before that, like just to give a high level overview that what I'm trying to do is like this is a very like I'll discuss about very simple things, which is like more around the reinforcement learning from human feedback, which is very popular today, and it has been there for a lot of years, but still it is very popular in the context of LLMs. And but what I'll just try to start is that motivation towards that, how my research went towards that when I was doing some research around reinforcement learning and reward design, and why I shifted towards RLHF, and how RLHF is more from a RL perspective. And then I also will explain the language model part of it, and then maybe we'll try to discuss about one key issue that I have realized that might occur or happen. And I think like since it's a little more discussion, so please feel free to stop and ask anything, whatever, if I'm doing something wrong. And these are like I collaborate with Amrit, Alec, and Mengdi and Furong, and from all I'm learning a lot. So I'm trying to do, yeah. So just to have a very brief introduction, I think it is not needed for all of you, but I'll still give that. What is reinforcement learning? It's nothing but where there is an agent, and the agent interacts with the environment. The environment gives it a new state or a new observation, and also a new reward when the agent takes an action. So the agent takes an action within an environment. The environment then returns a new observation and a reward, and then the agent, basically the objective of the agent is to maximize this reward. So this is what practically we explain. And then, so what are the motivations? So before just going to the motivation, I formalize the notion. So which is like the reinforcement learning setup is typically parameterized by a Markov decision process, which has a state, action, transition dynamics, reward, and a discount factor, which we can ignore. And the overall objective is thus to learn a parameterized policy, or a policy in general, which actually learns a mapping. So whenever you give a state, it will learn a mapping and generate an action. And so that is the policy that you learn. And a policy can be simply just thought of as some function, some neural network, whatever it is. And then the final objective is that I want to maximize a long-term reward, which is often called a value function in this context. And the value function can be simply defined as a sum of discounted reward function. So let's say I generate, so this expectation, I can simply think that I generate a trajectory and I collect some reward from the trajectory, and then I sum up the rewards, and then I get the long-term reward for that particular state. And then I try to optimize for that by some parameterization. And then the most popular algorithms that are used nowadays is the policy gradient algorithm, which is like nothing but a stochastic gradient descent with some minor modifications. With not only minor, there are some issues that this expectation has a dependence on theta. So it's not a typical modeling, but it's like more like where you have some specialized techniques to take the gradient. But once you're able to take this gradient, you can take an expectation, you can use Monte Carlo samples, and you can average it out and get an averaged out gradient. And then this is just like a SDT. So now, if we carefully see, what I realized is that everything else is more or less a part of the environment, or it is an explicit part of the environment. But something which is not explicitly a part of the environment is the reward. So reward is something that, like, it's not explicitly there in the environment. So it's like something that we need to design or know. So how do we know and what are the correct value of the reward function is has been a very critical point in robotics and RL in general for years. Like and then there is this issue of whether the rewards to be dense or it should be sparse. Now, the point is that let's if we think from a designer's perspective, then it's obvious that a sparse reward is very easy to design, right? Like, because what we do is we simply give the uh, a reward when the agent performs the task. So it can be a chess, it can be something very complex. But what we do is, okay, if you solve this puzzle, if you give, if you can traverse this maze, I'll give you a reward of 100. Else, everywhere, I don't care. Like, you learn by yourself. So that is the most easiest setting that is given. But on the other hand, dense rewards are much more easy to learn. So, I mean, if you have the proper direction that every step you get some sort of feedback from either some human or some reward model, that you get some feedback for every step that, okay, this is good, this is bad, this is good, then you will learn much faster. So from a designer's perspective, dense reward is very difficult to design because imagine that if the state space is very high, so if I'm not an expert, I will never know that at each point if he is doing right or wrong. On the other hand, sparse rewards are easy to give. But the issue is that when so in here at UMD, I was working a lot on some of the practical applications of robotics, and we were seeing robotics for manipulation or navigation. In various scenarios, we saw that rewards, sparse reward is a very big component, and it becomes a very big issue in learning. And for deploying RL to real robots, this sparse reward plays a very important role. And it's like people have spent like hours in tuning the correct reward function. So, and also we know that since reinforcement learning has this issue of exploration and exploitation, that how much to explore, how much to exploit, it's not very uh, it's not very easy when the reward structure is sparse. So what we realized is that when the reward structure becomes very sparse, then we see that this kind of the value function, or the, let's say, the loss function, you can think that it becomes some sort of edgy. Like, it's not very smooth that you can just simply apply gradient descent and it converges. So it becomes very, like, you can say that the function becomes very edgy, and there are some properties that gets violated in that way. And also, this is like a very well-known fact that we have also tried and seen that in a simple environment, in any environment, this follows actually, that if you increase the sparsity of the rewards, the performance degrades significantly. So this is like any algorithm, unless the algorithm is, let's say, some curiosity driven or some specific algorithm which is very designed to solve the exploration problem. So this is like, oh, just to mention, this is like a regret through the oracle. So it is like lower the better. So now as we increase the sparsity, the performance is clear that it's very bad actually. So the conclusion is that exploration is hard with sparsity. So how do we do it, and what are the steps? So one obvious step is that we do some sort of design of the reward function, or we do some sort of shaping of the reward function so that it can learn. Although we have, so it's like we have the true reward which is sparse, but can we do something which can shape the reward such as we get still some dense signal? So there are some very initial works around this. Like, I mean, in the context of robotics, these are little well defined, like curiosity driven, information directed, or Bayesian reinforcement learning. So these are more popular approaches that people use to solve this. So curiosity driven reward is so I'll not go into too much details into this, but curiosity driven reward is like, it's nothing that, but it's just that you augment your reward functions, right? So what you do is you say that, okay, for every state and action, the actual true reward is 0, right? Only when the state and action is the goal state, then it is let's say 100 or something. Other than that, at every state and action, the intrinsic reward, its extrinsic reward, or the true reward, is 0. So what the authors, or this is like not new, but still I'm saying that what they did is they said that, okay, let's see that how much uncertainty or how much confident the model is at those state and action. And you can get the estimate of the confidence by various methods. Let's say you see the uncertainty, posterior uncertainty, or epistemic uncertainty in some way, or you can see is like the prediction error for those state and action. And on once you get this kind of metrics, what you do is just you add this to your reward and optimize the policy for that. So what it means is it's just doing is it is saying the agent that go in the direction which you do not know, which you already know it, then let's explore the direction more, and let's see that if we can converge faster, and it actually converges faster. But one very important point I want to highlight here, which is often ignored, is that all this are like, this is good that the curiosity driven works really well in many cases, but also this is also true that when we add an augmentation to the reward function. So it is like basically we are augmenting our MDP in some way, right? So actually now instead of augmenting, optimizing the true objective, we are optimizing some false objective, right? So let's say we wanted to optimize V1, and we have some theta 1 that like theta star, which is the optimal for V1. Now we optimize V2. So there will be some theta 2 star that we get. So how do we ensure that theta 2 star and theta 1 star are close for any time point t? So one can always say that, okay, in the V2, what we do is we have some lambda t with the regularization, and let's reduce that over like at t equals to infinity. So when you reduce it exponentially or in some rate you reduce, and at t equals to infinity, you can say that that term will be 0. So you will be optimizing of the true objective. But interestingly, for sparse reward setting, that point does not make sense, because if you run for infinite time, then anyways you will converge, even if it is sparse reward or true reward, because like just think that if there are some n states, you can do all possible combinations. So doing some infinite time analysis in this kind of setting, it's not very sensible. So there are some recent works which does more provable ways of doing that. Yeah,
Can I ask a couple of questions?
please, yeah.
Okay, so first of all, if I am shaping my reward with a potential function, then the optimal policy will not change, right?
So my doubt is that so one thing is that so the common potential function that is used is that the difference between, let's say, the difference between the model's prediction error, let's say, between what S prime is being predicted and what is some ST plus 1, and then that error is added. So this kind of augmentations when you do, so it's like a new objective that you're optimizing, right? So how do I guarantee that theta star under that and theta star under my V are the same?
Okay.
So that was the doubt, but I
Yeah,
agree.
maybe that's because of the non-convexity as well, right, of the problem, I guess. Okay.
Yes.
Another question: have you had a look recently at this Eureka paper, which is trying like from NVIDIA, I think, and Eureka was trying to use LLM to actually design better reward. And yeah, have you seen that? And can you say a word?
I didn't see that, but yeah, that's a good reference. Thanks for that. But I'll so at a high level, what are their approach, like what they do?
Yeah, so in Eureka, what they do is this. So they give the environment as input, mostly like the state variable descriptions as an input, and then there's a true fitness in the real world. For example, you succeed or you fail. And then they use an LLM in order to generate code of reward functions such that you can maximize your fitness. And then they solve like very complex dexterous manipulation pen spinning problem using. Yeah, that was a pretty interesting maybe direction as well. Yeah.
Yeah, I think that's I think that's a very interesting point, and it's like it is some sort of that I am using the inherent knowledge of LLM as a prior to make my reward function dense, and then I actually update that. So that is very interesting direction.
Okay,
And
got.
and actually, yeah, and on those lines only. So I think when we use some sort of prior in this case, it comes under a very common framework of Bayesian reinforcement learning or posterior sampling reinforcement learning. And there are some very recent works actually which shows that if we explore in an information directed way, so what it means is it's very similar to the idea of curiosity, but it's in a more theoretical sense. But the idea is that, okay, if we can explore in a direction, where I get more information about some random variable E, let's say, and that E can be anything, like it can be the environment transition, it can be the reward or anything. If I do that in an information directed way and I use some specific algorithms, let's say a posterior sampling type of algorithm, then there are methods that we show that it converges the fastest. So so we did some work around this posterior sampling type of approaches where we show that with some nice kernel functions, we can show that it does really well. Like we can reduce, like even when popular algorithms become sublinear, we can linear with sparsity, we can show that it still maintains to be sublinear. But there are a lot of issues with such approaches. It's that most of these approaches are a little more theoretical, and also like it's hard to actually scale it for very, very large scale environments. For example, let's say even DM control suite or MetaVault. So that question actually, so we are trying to do that, but it is actually hard. And then I think what Adam mentioned, that now with this rise of LLMs, so it is natural that we should use LLMs as a source of prior and information. That maybe potentially, I have also seen a work, I think, which does is that you describe at every step, you can use a policy and you can actually use some sort of instructions from the LLM, so what you give is you give a description of the current position of the environment to the LLM, and the LLMs can actually tell you what kind of actions or what kind of small, like lower level trajectory to plan also. So that is also something. So maybe during training time, we can use that and learn the policy. And then maybe at test time, we can use that policy to deploy. So these are some of the things that are not directly related to this talk, but I just gave a high level overview to understand that like how this method of reward design was so motivating, because it comes from a practical perspective of actually truly deploying an RL system. So then what we realized is that definitely using some sort of intrinsic motivation based approaches is very interesting. But there are a lot of human preferences or feedback data that are already available in the market. So for example, what we realized is that there are various ways to learn a policy in this kind of sparse setting. One is demonstration, which is very obvious that if you have like an expert has kind of given you the optimal trajectory for every, let's say, start state or something. So in that case, it's obvious that if you have infinite data, with likelihood you will converge to the optimal policy, which makes sense. But then there are some criticisms that getting demonstrations is much more expensive and it's not very practical, and only experts can know. But then there is another framework or paradigm, which is like more like human preference based or feedback based learning. So what is the advantage of this is, here you do not need to give an expert demonstration. What you need to do is, given any two trajectories or given any two responses in the context of LLMs, I'll tell that. So what you do is you simply compare. You just say that, okay, A is better than B or B is better than A. You compare and you do that for multiple trajectories. And then you learn policy by some method. So there are multiple methods to that. That also is fine. But you can learn a policy which does actually better than, given the obviously it is a function of the suboptimality in the preferences, but in general what it has been studied that is that giving preferences, it's much more easier than doing a demonstration. So we can get a lot of data of preferences. And I feel, according to me, this is one of the main motivations that RLHF is being used, and also it is being scaled, and a lot of people are finding a lot of benefits from this. So now this brings to the main problem of reinforcement learning from human feedback, and what I think we all now know about this framework, but still I'll introduce this framework once. So what we do is, in the outer objective, so there are, let's say, two objectives. In the first objective, what I do is I get preferences from some human by showing some trajectories. And then based on the trajectories, the human gives some preference. And then what we do is we learn a reward function from that. And based on that reward function, what we do is we learn a policy which can optimize. And if we do that iteratively, we can show that it converges. Like, I mean, it was not yet shown that it can converge. So empirically, it does. That was the main hypothesis of RLHF. And it was actually introduced, like the reinforcement learning for preferences or in the context of RL was, I think one of the first papers was by Cristiano's group in 2017, 16 or 17 and around. So now let's just to briefly explain that what happens is we start a policy. So let's say we start with some random policy, we collect responses or trajectories, then we collect human feedback, learn a reward function, optimize the reward function, then learn our policy in that reward function, and then we actually do that iteratively. And this is so this is like for any general policy or any general model, it will work and it holds. Now, in the context of language models, how it has been defined is in this way, that now what happens is, now your policy is nothing but a language model. So it can be like, let's say, a llama or some GPT-4, and a reward function and a reward model is also a language model. So basically, like what people do is, like, you have some initial language model, which we call it, let's say, SFT. So the SFT means supervised fine-tuned model. And then we generate some summaries or responses. And let's say we have a fixed set of prompts. And then we generate some responses from those fixed set of prompts. And then what we do is we pass those responses to human. Human sees those responses, and it is very comparatively much easier for human that when you give two responses, that it will react that this is A is better or B, and then you get those responses, learn a reward function, and then you update a policy using reinforcement learning. And this method from OpenAI, so I'll like, I have missed some citations, I'll cite. So, but this is like one of the most commonly and most popular frameworks that is working today, and even ChatGPT or any popular LLMs which are called aligned are based on this kind of a framework. So now let's see, like, mathematically how it is working. So when we see that, so first of all, we know that, okay, so first question is that when we have a human preference given two trajectories, so let's say we have two responses, and okay, and interestingly, in the context of LLMs, we think of a setting where there is a prompt and there are two responses. But in the context of reinforcement learning, it is the same thing, but it's just like two trajectories. So many a times it's little confusing because of the notations and all, but it is basically the same thing, and there is no new thing in that way. Only one thing I can ask, or maybe what I think is that what is the true notion of a prompt in the context of a robotics or reinforcement learning, typical reinforcement learning. So one thing I can think of is, although it is not very clear, and please point me if there are some things that you think it is different, but I feel that very lightly I can think it as some initial state distribution or initial state. Other than that, it seems, or it can be thought of in a goal conditioned way also, that as some goal or something. But at least very broadly, I can think it in a simple way is some initial state, and these two are the trajectories. So now what happens is, given a response X, what we do is we collect two trajectories or two responses. Given a prompt X, we collect two responses, Y1 and Y2, from the language model, let's say. And then what the human says is, this human gives a preference. Now this P star represents the preference probability of the human, because like we assume that there is some stochasticity, can be due to various reasons. And the most popular way of modeling is this, that what we do is we have this P star, Y1 greater than Y2. And what we do is we actually express this using this Bradley-Terry choice model. There are multiple other models. There is this Placard-Lucet model, which is more general version of this. But for simplicity, let's assume that given this prompt X, when you have Y1 and Y2 greater than Y1, then what you do is you simply just take this exponential of R star X1, XY1 divided by XY1 plus XY2. So what it means is, this is the prompt, this is the preferred response, and this is the rejected response. So what it means is nothing that you want to learn. So when we are learning the reward function, so what it means is we want to learn a reward function in such a way that when I give the X as the prompt and Y1 as the response, the reward is high. If the human has said that Y1 is a better response than Y2, else, and you make the other reward as low. This is the very simple intuitive idea of this. And now once we expand this, so basically what we do is then we maximize this using a likelihood function, which also you can simply see that it can be a cross entropy. And if we expand that cross entropy, so cross entropy meaning just like expectation P star and log P5. Now, when we expand the cross entropy, And we will exactly boil down to this kind of an expression where this is nothing but the log sigmoid of the reward difference. So this is, and we are in a parameterized regime. So this R phi represents the, let's say, a single valued reward function. When you give an X and when you give a Y, it will give you a single valued reward function. Now, one thing to note is that there is something called, like, let's say there is a transitivity in the preference. So let's say if there are two, let's say there are three responses, A, B, and C. So let's say some human has told that A greater than B and B greater than C. So then naturally, this kind of a model will actually tell that A is greater than C. But in case when the human, and it has been commented that human preferences is not necessarily always transitive. So this kind of a single utility based or single reward based model, which actually just gives you a transitive response, it cannot be able to model that. So we need to think beyond that. But for now, let's assume that this is the most basic setting of this framework. So now once we have this likelihood loss, we know that we can simply take gradient descent and learn the learn a
I'm
phi.
sorry.
Mhm.
I'm sorry, Suradip. Sorry. Can I ask a quick question? I think
Please.
it's related to what you said about this non-transitivity.
Yes.
If I remember correctly, in Instruct GPT, they assume more than two basically instances for comparison. I think they do the rankings of four or five. So can you please say something? How would you generalize that formula? If, for example, I want to say that y1 is greater than y2 is greater than y3 and is greater than y4, if this non-transitivity is present, do we have
Yes.
any generalization?
Yeah, that's a very good question. And now, okay, let's say, so one way I can think of it. So for me, I think there is no way to generalize that directly, at least, or maybe I'm not aware of that. But maybe let's say one way of thinking of this is in this way. Okay, like how I can think is this. So it's like this. So let's say, let's say you have some preferences of A greater than B and B greater than C, and then there is some other preference which actually it's like kind of opposing these views. So maybe let's say C greater than A. Okay. So let's say there is one preference of this sort and another preference is this sort, right? So in when I go think of by modeling using a single utility model, these two are conflicting preferences in that way, right? Because the natural extension of this is A greater than C. So interestingly, what I think is that what one can do is we can always learn one utility for this and another utility for this. And then it boils down to how do we combine the two utilities to learn something meaningful. But if it is, but it's clear that in this case, this is still conflicting. And I'm not sure that still there is one general solution for everything that can satisfy all these things or not. But maybe we can do something like based on some context. If we assume that there is a hidden context, then we can, so let's say there might be some hidden context that because of that x which is causing this type of conflict, and then based on that context we can make a prediction.
Gotcha. Yeah, gotcha. Yeah. Thank you.
Yeah. Yeah, I mean that I can think of, but there is another work which actually, so there is a work of called Nash learning, right? Nash learning from human feedback and those direction. I think it was originally proposed by Chizin, which says that let's not model this in a parameterized setting. Let's model this as some sort of a matrix. And then there is a little more flexibility in that way. But how practical that setting is, I'm not yet sure, but maybe we need to explore that a bit. But yeah, but this is like, as you mentioned also, and this is like a general issue of this approach. But let's assume that still we are in a good setting where there are no intransitive preference. So then this becomes like, okay, this is a simple likelihood maximization problem, or in this case, minimization. I minimize, I learn a phi, and everything is good. Okay, so one sec. Yeah. And then the next stage is the RL fine-tuning phase, which I think, again, we are all very familiar with that. So there is a parameterized policy pi theta, and there is a parameterized reward function, which we have already learned in the previous stage. Now I learn the policy by doing whatever I want to do. But this particular objective, if you see, it's a very similar objective to the most vanilla version of the RL problem, which is like some sort of reinforce. objective. So there was some confusion about this also. I see some discussions, but what according to me, how I think is that, so this is okay. Let me clarify that this notations are now, which I have copy pasted, is actually in the context of a language model. Okay, and it's not directly a context of a RL problem. But so how I can think it is this, that let's say this pi theta, right? So, and this y. So y is what? So y is a response. So y, I can think y as a sequence of multiple tokens, right? So y1, y2, and y capital T. So let's say I can think it as a sequence of tokens, right? So in the context of RL, what it means is it means that it is nothing but trajectory, right? So this is just a trajectory, tau. And we all know, like we all who work on the field of RL, we know that we can simply express this as a rho, which is, let's say, the trajectory distribution, which is parameterized by the policy theta. Then what happens is I'm sampling one trajectory and I'm maximizing the reward of that trajectory, right? This is nothing but reinforce, some version of reinforce. Not, there are different versions, but like, let's forget the discount, etc. But this is simply that. But when in the context of language model, people often tries to say that, okay, like this can be simply thought as a policy which takes a prompt as an input and gives you a response, right? But and then another question comes is that, okay, whether it is a contextual bandit or it's like a RL or whatever, that there are a lot of debates that are going on. I don't want to go into those debates, but it seems like theoretically, of course, like if you have a context, you can actually have an arm, and you can think in theoretically or fundamentally this problem as a contextual bandit problem. But there is an interesting perspective is that in this case, right, you cannot generate, if you think from a practical perspective, we cannot generate a response directly from a sampling from some distribution over the arms, right? It has some Markovian structure inside it, and we have to generate using like sequential sampling. So I have to generate, like, I get y1, then I sample, given x y1, I sample y2, then, and like that only I can sample y. So to me, it is much more closer practically to a setting where it is reinforcement learning, where at a token level. But since the reward we get at the end, when I have generated the entire response, because it does not make sense that at every time point you generate something and you get a reward. You cannot do that. Only that is the reward. So one can think in various ways. But for me, that is how I feel, that as a token level MDP is the most simplest way to think. And practically also, when you see the implementation, it is actually happening at a token level as well. So this two things are aligned in my head. But yeah, still it is an out of context distribution. I don't need to talk about this that much, but this is the idea. So this is the RL fine-tuning phase. And if we can simply parameterize a policy using theta, I can learn this and get a theta. So this is also good. And okay, and there is a context of a reference policy, which is like, okay, in the context of RLHF in LLMs, people use this because we know that there is a pre-trained LLM which is very nicely trained, and I just don't want to overfit to my reward function too much so that I lose all the utilities that I have trained before. So that's, and this beta term controls that. I feel there is very less discussion on these beta terms also, and I feel that this beta term is more domain specific. But yeah, that's also another thing. So what this beta terms does, it's nothing but it just kind of describes the radius in which you want to bound this policy. So it can be thought of as some sort of a 1 by beta radius. So yeah. So this is the overall objective of the RL problem. But what we have seen is that when we are learning from a static data set, it is fine, that there is no issue. Probably we can do the standard framework. But when we do it in an iterative way, there are some critical issues that might have been highlighted in that might have been missed in the case of when we do in an iterative fashion. So so what we okay, so there are three environments that are like, basically there are 2-3 setups. So I have not emphasized a lot on the setup, but there are environments like DM control suite and meta world, where there is a setup which has been generated like a RLHF way, and it has been like it has been practiced from like the Cristiano's paper, and then there was Pebble, Surf. So all those papers have used this kind of a setup, and they have been trying to do this RLHF for robotics type of tasks. So what we have seen is that when we do those algorithms in the most simplest way, that we do not use any fancy, like even we use fancy techniques of sampling, etc., but that does not help. But we do it in a simplest way. There is a gap between the true reward function that is achieving and the current SOTA method like Pebble, which it achieves. So we realize that inherently what is happening is inherently the problem of RLHF is very entangled. So there are two objectives that we learn, which is the outer level is learning the reward function, the inner level is learning the policy, but those two objectives are very, very much entangled. So how by entangling, what I mean is this. So when you have a policy, so first of all, you start off with a reward function, let's say R naught, then you actually solve optimally for that policy, pi naught, right? And then what you do is you generated these trajectories from this policy. Now, interestingly, if you see that when you generate these trajectories are generated by pi naught, which is solved under R naught. So these trajectories also depend on R naught, and it is not free from R naught if we are learning we are learning with iterated gradient steps. And then what we do is we again minimize the reward function under these trajectories by collecting human feedback. And then we learn the reward function and then the policy in an iterative fashion. So what we try to see is let's clearly see that what is happening here in the optimization objective. So let's say that at any iteration, we are at the iterate t, and let's say r nu t represents, so sorry, I had used phi t before and nu t now, but just for the sake of simplicity, let's assume that R nu t is the parameterized reward function, which is parameterized by nu. So now what we do is under this, so at any iterate, let's say I start with R nu t, right? So what I do is, and this I'm talking about all the ideal cases, like we can do a lot sort of approximation, but that does not change things fundamentally. So let's say we start off with R nu t. Then what I do is I solve the optimal policy under this R nu t. So let's represent that optimal policy as pi, which is like theta star nu t, where theta is the parameter of the policy. Now it is important to note that this theta star nu t is a function of nu t, and it is not independent of nu t. So now what we do is once we have solved.
So Radeep, sorry, what does pi of theta star mean? Because, or do you mean pi is indexed by theta star?
Yeah. I agree that this notation is a bit loose, but what I just mean is this pi is parameterized by this theta star nu t.
Okay, I got it.
Yeah. It actually will be like it eventually. There should have been a subscript, and then it would be like this a given s. So this will be pi of a given s only, but the parameterization is theta star of nu t. So now in this setting, what we do, so now once we have optimized for this policy, what we do is we now collect trajectories, right? So what we do is we collect trajectories from this policy pi theta star nu t. So let's say we sample two trajectories from this tau theta star nu t, policy parameterized by that. And then what we do is we optimize for the loss function under that theta star nu t. So for learning the next iterate nu t plus 1. So what I mean is when I'm learning this nu t plus 1, for the next step, what we do is we actually solve for this objective. So let's say I sample a lot of trajectories and get preferences using this policy, which is theta star nu t, right? And then then the outer objective is some sort of this, where these are modeled by Bradley-Terry functions, and we can get those as functions of nu t as well. So basically, to summarize, what happens is you have an expectation where there is an implicit dependence on nu t. So it becomes an implicit dependence of nu t, and then there is an outer objective where there is an explicit dependence of nu t. Okay. So basically there are these two versions, but interestingly what we observe, and I think what is common, is when you take the gradient of nu with respect to this objective for performing gradient descent, you like most of the time what happens is people forget this term. They just take samples from this distribution, or basically they say they take the samples from the trajectories, and they compute this function. They compute this function value. And what they do is they take the gradient of this loss with respect to nu, and then they update nu by doing gradient descent. So this is the one main thing we realize, that once we do this in an iterative fashion, this term actually we cannot ignore, because this is an implicit function of nu t, and we need to take care of that while taking the gradient as well. So once we have realized this, then we realize that, okay, in this setting, if this is happening in this iteration way, what is the correct way of writing the optimization problem, or what is the optimization problem that we are actually solving? So what we realized is this optimization problem can be written in this form, which is the most general way of writing the optimization problem is this. So I have some objective that I want to maximize, which is a function of nu and theta star nu. So there is a term called theta star nu here, and theta star nu is solving this problem. So this actually comes under very broad optimization field of bi-level optimization, or also it also is like a Stackelberg game. So that where there is a leader and there is a follower. So the leader takes a move, the follower optimizes under that move, and then gives feedback to the leader, and things happen. So, or in other words, and from the optimization perspective, it is like a bi-level optimization, which means that your outer objective depends on the optimal solution of the inner objective. And as we discussed, that this is basically nothing but this objective in the case of RLHF. So this has broader applications, but let's say when we take the case of RLHF, we can simply just replace this objective, and this will be my problem that we can solve. Now, so now once we have this is the paper that we wrote, and we had some, like, basically we will be presenting this ICLR also. So once we formulate this objective, as I mentioned, that this is like a way of representing the most general version of RLHF, which has this kind of a dependence, which is explicitly made clear. Because many times what happens is we can actually deal away with this dependence by various ways. It's like I collect very huge amount of trajectories from a lot of policies, and somehow we can agree. When I take expectation, many things can happen. But from a language model perspective, or this kind of now that RLAIF type of approaches are getting more popular, it's like it shows also that so we can do these things in an iterative way. We sample from one policy, get some feedback from some language model or somewhere, and then I update iteratively. And whenever I'm doing iterative update with this type of sampling from the optimal policy in the inner loop itself, there will be a dependence which we can't ignore. So this was one key finding that we figured out. And then what we do is we characterize this, basically this distribution dependence of this. And this falls into a bi-level optimization, but this also falls into a very special class of bi-level optimization, where the expectation is dependent on the optimal policy of the inner loop. Because in normal bi-level optimization, what happens is that it is like these things are independent. These are like basically IID noise. And there is theta star nu dependence somewhere in the function itself. But here what we realized is that theta star nu dependence in the expectation. So this is like a new class of bi-level optimization problem, although there are some works that has addressed this. So what we do is, and now in the bi-level optimization problem, once we know that solving the inner loop, at least till iterate t or something, is not a big issue. And we know that, okay, if I can solve the inner loop with till t iterations, I know that because of the I can assume some structure in the RL objective, and then I can have some sort of upper bound in terms of the saddle point of the objective, or let's say the convergence rate in that way. But what challenge is this is that in this case, how do we compute the gradient of the outer objective? So maybe I do not want to complicate too much by going into this, but it is very simple in that way. But only there is one thing that comes down is, like, let's say when we expand this objective, then it's just like we do a chain rule. And when I expand the chain rule, there is one term comes, which is this. So which is basically the gradient of the score function with respect to the reward parameterization. So this is a very, very interesting term that we realize that if let's say I am a reward designer and I want to design my reward function nu. So if somebody could tell me that how is this gradient, like basically if somebody can tell me that given this reward function nu, how my policy will behave in a way, then I can very easily, quickly, directly design the reward function. So it's something like this, that if I know that for pi1, this is my behavior, this is the change that will happen. And for nu2, how the policy will change. That change in policy will gives me a lot of very easy information to quickly design my reward function. And so this term is very critical if we can have access to this term. But it seems that computing this term is not very easy, and we need some sort of approximation, which is like basically the implicit gradient computation in bilevel, that we can that we do some tricks and we get around these terms. But it seems that there are some complex dependencies of Hessian and Hessian inverse that are coming, which we actually bypassed using some approximate methods like, so there are some lot of libraries that are designed for bilevel optimization, like TorchOPT and this type of meta gradients type of approaches. So we use those kind of heuristics for now. But later we have realized that there are better efficient methods of first order to solve that, which we are working on. But what we realized is once we use this, then then our algorithm is very
Suradeep, can I ask you one question?
sure.
I'm very, very worried about the scalability of your method.
Sure.
Because if you need to compute Hessians and Jacobians,
Yes,
right?
Yes.
This is very worrying, right? And we've been working a lot on scalable, second order methods and so on, and nothing really seems to scale well, right?
Yes.
So
Yes.
is there a way to avoid all these altogether, or something?
Yes. So so that's a very, very crucial and very important point, and that is like I think everybody will be like very cautioned about this. But what we used, at least for this implementation, is that what we realized is we do not need to explicitly compute this type of inverse product type of terms. Rather, what we can do is we can use some sort of implicit gradients, like what is it called? It's I think. So what it does is it does not explicitly compute that, but it actually uses the PyTorch method, and it takes the like basically it's like stores some previous iterate and just does some approximation by iteratively multiplying the gradient. So these maybe I can explain in a better way how to do that. But I think what
Well, I think what people do when they need to compute Hessian vector products is like there is a way how we can compute Hessian vector products using
by the
just a fit form.
The Newman approximation, you will say, right? Like I make a X transpose AX type of form and then solve that in that way, right?
Yeah. But what I'm confused is this. This is about Hessian vector products. You can indeed approximate that using just basically reducing that to computation of the gradients. But you have a Hessian inverse, and this is not very much Hessian vector product. You need somehow to represent this Hessian inverse in terms of the Hessians, and then apply this Hessian vector product trick. That's.
I think you can write this as a system of linear equations where A is the Hessian and use conjugate gradient or something.
Yes, that's what I was saying. Yeah.
Something like that.
Yeah, exactly. Like that conjugate gradient method is there, and we can, because it is convex, we know it will solve and we'll get this. But another method is there, like this, there is a package, and there are some packages actually what it does not go to this expansion. What it does is it saves, like basically it just does some iterative multiplication and approximately computes this term directly, so without expanding. So this term or maybe this term, so they are directly try to compute that. I'll just show you, maybe if after this I'll show you. But having said that, just to give a very brief primer, that is this, like this problem that we are solving. Indeed, it seems that we need this kind of expansion, and in this paper because in this paper we mainly focused on giving this formulation or generalized formulation. So we were a little bit not very careful on the computation side of things. But in fact, we know that solving this bilevel optimization problem, now we can actually formulate this as a constant optimization problem as well. Okay, and once we can formulate this as a constant optimization problem, we can show that using only first order methods, only first order gradients, we can exactly get the solution, which it will be a little slower than the second order, like slower in terms of the convergence rate. But still we can actually get the like very good solution with first order methods only. So so maybe I wish I did not add that slide because we are working on that. But the very simple idea is this. Let's say if this is my objective function, theta star nu, and the inner problem I can actually write as some sort of f of x theta minus f of x theta star nu less than or greater than equal to 0, depending on the inner is max or not, less than equals to 0. And sorry, the upper bound, we can still make it theta. So it is like, it becomes like minimize nu comma theta, which are now not entangled variable, minimize nu theta of the upper objective. And then the constant, we write it in this way. And using this method, we can show that we actually get rid of the Hessian. And with only first order methods, we can actually converge. So that is also there. But I did not like emphasize too much on this to highlight the formulation, but that is there. And maybe we'll also discuss, expand on that.
Okay, nice. So you are saying there is a way, right, to scale your method by
Yes.
just doing first order
Yes.
optimizers, right? Okay, yeah, cool. So, okay, yeah, this is awesome. Yeah.
And once and it's almost done. Sorry, I'll not take much. I think we are there almost. So what we do is once we actually use those methods and we scale it, and we show that when we actually work on this kind of environment. So I have results for both the TM control suite environments and the meta world environments. We see that actually we can outperform both this Pebble and Pebble plus data augmentation, Pebble plus search, which are the current state of the art methods with RLHF for robotics. And we can see that it actually works. And it tries to mitigate the gap by good amount and being very sample efficient. So it kind of works practically. Yeah, there are some issues that we are still dealing with in terms of the scalability and all those things, but it's at least in this kind of environments where we have an iterative feedback, it works. So we tried to like take some. So now what we are doing is we are trying to see that if it makes sense in the context of language models also. But yeah, like that's pretty much what I have been working on. Yeah.
Amazing. This is um, so thank you. And this is amazing work, Suradeep. I'm very excited about your career going from here. Well done. This is really, really cool stuff. So we also have some audience in here. I don't know if anybody would like to ask any question of Suradeep. If you have a question, please go ahead.
Sure. But thank you very much, Hatham, for this opportunity. And I know I have like skipped some parts and maybe bit but I was trying to slowly explain step by step. I hope things made sense and I tried to explain that point. But yeah.
It was amazing. Yes, definitely. Cool. So I'll definitely look forward to the scalable extension of this. Actually, so this sounds really, really nice. And we just end typically those lectures with asking a controversial question to researchers to see your view. So so we all know that the review system we have is a bit of a mess in the community. So how was your review experience at these conferences, and what was the worst one, and how do you think we can improve the review process?
Yes. I think I genuinely feel I know that you have been always very much concerned about that, and we have like had discussions. But I also want to emphasize that I have had mixed reviews. But I feel I want to say something about it. Maybe I'll take 3-4 minutes. So one thing I want to say that, like, let's say when I am working in a very, very niche area, let's say posterior sampling. So I know that these are very rigorous people who work and they are very critical and they want to, like, they will review very nicely. But then when I, let's say, shift to a very empirical area, like let's say, and doing some experiments with some intuitions, I will get some reviewers who completely think like her perspectives are very different. Like they are just saying, oh, this is intuition. So I think I have also got mixed reviews because there are some reviews who just says that, okay, this is little nice idea, but what if, why don't you try on this 100 experiments? I mean, this is a very common thing. So I think that is what very, like, because I think this is happening because of the mindset of the people, like different people think differently. So I feel that if we can, what if we can, this is my proposal, I really want this, that what if we can segregate the papers, that this paper is more about theoretical perspective, this has both theory and experiments, and this is just empirical. And we make some sections and we give those kind of reviewers, because if I get 6 papers which are completely theoretical and somebody gets 6 papers which are just doing some experiments with intuition, both are good, but I'm saying that it is not totally fair also that you give the same time so these things plays a big part.
Right.
And another thing I feel, it's a little controversial question, is that it's that I mean, since we are already in a crunch, in a situation where we cannot get reviewers, so we cannot penalize reviewers, right, if they give bad reviews. But there should be some either incentive or penalty that should be given. Like if I am continuously reviewing very badly, like just putting into ChatGPT and all. So, but if we just made a penalty that you won't be able to review, that is not helpful. So is that like, does it make sense that maybe there will be some sort of negative feedback on that, or some cutoff on the paper submissions that you do? Possibly. So somebody can say that, oh yeah, you are stopping science, but then they can always post it in archive. So
Interesting. So your idea on that side is, if I do a bad review, then for the next 2 conferences or something, you restrict my my submissions, something like that.
Maybe that might not be that as strict as possible, but maybe let's say if you do review in 10 conferences, right? Because it seems like you are also doing harm to science, right, by doing that. So it's not good. So something we are thinking, but I know that there are a lot of things that people work a lot hard for writing their papers, so, and stopping them, because PhDs are very dependent on acceptance. So I can feel that. So that's why I also feel that's not a practical decision, but something around those, maybe rather than the penalization, what if we increase the incentive side and see if we pay them?
Maybe. Yeah, exactly. Yeah. Makes sense. Cool. Okay. Thanks a lot again, Suradeep. This was fantastic. So to our audience, please join me thanking Suradeep by having a like, share, and a follow, and subscribe to the channel. And I will see you again with another fantastic researcher the next time. Thank you all for watching.